Hello, good morning. So today we will solve the quiz number 2 in chapter 22, which is about electric fields. So as you know, when you solve the problem, give the main detail of your calculation, and of course, you circle the right answer for full mark. Let's begin. Question number 1. The electric field midway 2-point charge of plus 3Q and minus 2Q is 98 Newton per Coulomb. And the distance between the charge is 30 centimeters. Find the value of the charge Q. Of course, you draw the problem. You are in physics, you draw. Let's start. So let's assume that this is my x-axis, straight line, and this is the origin, and this is the x-axis. Let me put everything in meters. Okay, so charge 1, let me call it Q1, which is equal to plus 3Q is right here. So the positive charge is at the origin, let's say. And charge Q2, let me take another pen. I call it Q2, which is equal to minus 2Q, and it's negative. Charge 2 is negative, and it's here at 30 centimeters from charge Q1, basically at 0.3 meters from charge Q1. Now I'm telling you at midway between the 2-point charge at this point here, which is right at the middle, which is at 0.15 meters, I have a net electric field, which is 98 Newton per Coulomb. So E net in magnitude is 98 Newton per Coulomb. So remember, E net is equal to what? Principle of superposition. Net electric field is the electric field created by charge 1 vector plus the electric field created by charge 2 vector. Now, the electric field created by charge 1, let me put it in red. Here at the middle, it will be pointing radially away from charge Q1, which is positive. So this is E1 vector. So by the way, what is E1 in magnitude? It will be just K, absolute value of Q1 divided by the distance between the point at which I'm looking at the electric field and Q1, which is 0.15 squared. This gives me nothing but K 3 times Q divided by 0.15 squared. So that's for E1. What about E2? I want the electric field created midway by charge 2. Charge 2 is negative, so it will be pointing toward charge 2. Let me put it in blue, for instance, to show you the difference. So E2 is pointing towards charge 2. Yes. Charge 2 is negative. Charge 1 is positive. Electric field pointing away from charge 1. Charge 2 negative. Electric field pointing toward charge 2. What is the magnitude of E2? K, absolute value of Q2 divided by the distance between Q2 and the point, which is 0.15 squared, which is nothing but K 2 times Q divided by 0.15 squared. So if I want the net electric field, I have to add these two vectors. Let me project this along X. The net electric field, which is E net along X, both E1 and E2 are pointing in the same direction. So it would be plus magnitude of E1 plus magnitude of E2. Both electric field are pointing in the same direction. So it will be K 3 times Q divided by 0.15 squared plus K 2 times Q divided by 0.15 squared. This gives me 5 KQ divided by 0.15 squared. And this E net has to be equal to 98 Newton per coulomb. So that Q is just 98 times 0.15 squared divided by 5 times K, which is 9 10 to the power. You do the calculation properly, of course, you get Q, which is 4.9 T 10 to the power minus 11 coulomb. So B is the right answer. You do it, you have to. Let's move to problem number 2. Now in problem number 2, we have point charge Q1, 10 microcoulomb, and Q2, minus 10 microcoulomb, are separated by a fixed distance of 2.5 millimeters. This electric dipole moment, of course, plus Q minus Q separated by a distance, small distance, is electric dipole. So this electric dipole moment makes an angle 30 degrees with a uniform electric field of strength 4 10 to the power 6 Newton. Okay, so find the work done by the external agent applied by you, let's say, to rotate the dipole moment until it's anti-parallel to the field. Okay, let's draw the electric field. This is uniform electric field. These electric field lines are parallel to each other and they are equally separated. So this shows you that this is a uniform electric field. The magnitude of the electric field is 4 10 to the power 6 Newton per coulomb. Now I have my dipole moment, let's say minus Q. Here I have plus Q, electric dipole moment, which is characterized by the electric dipole moment P. So this electric dipole is characterized by an electric dipole moment P. And P is plus QD, goes from the negative to the positive, right? So in magnitude, P is just Q times D. Q is 10 to the power minus 6 coulomb, and D is 2.5 millimeter 10 to the power minus 3. So this is my electric dipole moment. Now it makes an initial angle, theta initial, of 30 degrees. Now I want to make it anti-parallel to the field, meaning this guy, I want to rotate it in this direction, such that the electric dipole moment P is in this direction, anti-parallel to the electric field E, which is in this direction. So my theta initial is 30 degrees, and my theta final is what? 180 degrees. Now we want to calculate work applied, or work done by the external force. And work applied, as we studied, is plus delta U, meaning it's U final minus U initial. Now what is U final and what is U initial? You know that U is minus PE, the product P dot E, which is minus magnitude of P, cosine the angle between them. So you know that U final will be minus PE cosine theta final, which is 180 degrees. So this is nothing but plus PE. Then U initial is minus PE sine 30 degrees. And the difference between U final and U initial, the difference with delta U is just PE 1 plus cosine 30. Don't forget it will be minus minus. Okay, so let's do the calculation. The work applied is P, and I know P is QD times E times 1 plus cosine 30. I know Q. Q is 10 to the power minus 6. I know D, the distance between these two charges is 2 10 to the power minus 3 meters. Because I put everything in SI units. I know E. What is E? 4 10 to the power 6. And you do the calculation, and you will find this answer. D is equal. Let me write it properly. It will be 0.187 joule, in other words, 1.87 to the power minus 1. So D is the correct answer. You do it, you have to mark. Let's move to the next question. Recharge Q1, Q3, and Q2 have the following values. So Q1 is minus 2 microcoulomb. So Q1 is here and it's negative. Just throw it here. Q3 is also negative and it's equal to minus 2. Same magnitude as Q1, same polarity. And Q2, which is right here at the origin, is positive. And it's equal to 4 microcoulomb. So this distance here is 3 centimeters. Plus this distance is 3 centimeters. And the question is, find the magnitude of the resultant electric field, meaning E net. Find the magnitude of E net at point P, which is at coordinate 0 along X and 4. Wow, 4 centimeters. So this distance here between P, the origin is 4 centimeters. Okay, I want E net at P. So we want E net at P. E net at P will be E1 at P, electric field created by charge 1 at P, plus electric field due to charge 2 at P, plus electric field due to charge 3 at P. Principle of superposition. Now let's draw the electric fields. Okay, so let's connect the line connecting Q1 and P. This is the first line. This is the second line. The third line first. This is the third line. Okay, good. Now E1, Q1 is negative, so it will point towards Q1. So electric field is going in this direction. Let's say this is here. This is E1 at P. E3 at P is going in this direction. This is E3 at P. So it's not really nice, but you understand that this is E3. Electric field created by charge. Do we all agree that E1 in magnitude is the same as E3 in magnitude? It's equal to K, the absolute value of minus 2 microcoulomb. We put it in coulomb divided by the distance square. What is this distance square? Well, the distance between Q1 and P is the same as the distance between P and Q3. Use Pythagorean theorem. If this is 3, this is 4, so the hypotenuse is 5. 3 squared plus 4 squared is 5 squared. So the distance is 0.05. I put it in meters squared. So this is 9, 10 to the power 9 times 2, 10 to the power minus 6, because it's microcoulomb, divided by 0.05 squared. You can calculate the value here. And you see the magnitude of E1 is the same as the magnitude of E2. Let me just notice E1. What about the magnitude of E2? I mean, magnitude of E1 is the same as magnitude of E3. Now, magnitude of E2 will be just K, absolute value of Q2 divided by the distance between Q2 and P, which is 0.04 squared. You can do the calculation if you want. So Q2 is 4 10 to the power minus 6, and you divide by the distance. Right. What will be the direction of E2? Q2 is positive, so it will be pointing upward. This is E2. Okay, right. Now let's do the vectorial sum. First, we can see that E1 plus E3 will give you 0 along X. So they are opposite. You can see the X components are equal in magnitude and opposite that. And 2 times the Y component. So let's do it properly. E1. What is E1? E1, you can see that it's in the third quadrant. So it's negative along X and negative along Y. Now this angle here, let me call it theta. Let me take another color of the pen. So theta is this angle here. And it's this angle here. All agree. Now what can we say about theta? Well, we can say that tangent theta is equal to 4 divided by 3. So theta will be tan inverse of 4 divided by 3, which is 53.1. 53.13 degrees. That's theta. What is cosine theta? Right, easy. Cosine theta will be just 3 divided by 5. What is sine theta? It will be 4 divided by 5. Good. Now E1, what's the component of E1 along X? It will be magnitude of E1 cosine the angle theta. What is the component E1 along Y? It will be magnitude of E1 sine the angle theta. What about E2? E2, I mean E3. This E3 here. It's positive along X, and it will be equal to E1, which is the same as E3 cosine the angle Y. So this angle theta is the same as this angle. And along Y, it will minus E1 sine theta. Right. What about now E2? Well, E2 is negative, is 0 along X, and along Y it's just magnitude of E2. Let me add all these vectors. E net will have a component along X, which is this, plus this, which is 0. You see, they cancel. These are the X component, they cancel plus 0. So it's 0 along X, as we said at the beginning, because of the symmetry of the problem. See, when you look at the symmetry of your problem, you can guess what will be the net electric field. Here, the net electric field will be along the y-axis, because Q1 and Q3 are symmetric with respect to. And when you add, you see it. When you do the calculation, you see that it's 0 along x, and along y, you have minus 2 times E1 sine theta plus E2. Wait. So let's do the calculation. It's 0 along x, and along y, you have minus 2 times E1, which is this number here. And you can do the calculation. Sine theta, you all know sine theta. Sine theta is sine 53.13 degree, or you can just say sine theta is 4 divided by 5 plus E2, and you can do the calculation. E2 here, denominator of E2. You do it, you get 0 along x, and along y, you will have 1.1 10 to the power 7 Newton per coulomb. So the magnitude of the net electric field at point P is just 1.1 10 to the power 7 Newton per coulomb, which is this answer I. Good. When you do it, you get full mark for this question. Full mark for draw, draw, and you do the calculation properly. Last but not least, we have a proton, and we know, you can check from your formula sheet, that is the mass of a proton, 1.67 10 to the power minus 27 kilograms. That is the charge of a proton plus E, meaning 1.6 10 to the power minus 19. It's a proton, which is positively charged. So the proton moves with the velocity of 3.80 10 to the power 6. You see here, I'm giving you 3 significant figures. I want my final answer to be in 3 significant figures. 3.80 10 to the power 6 meters per second in the positive x direction enters a region of uniform electric field parallel to the x-axis. Let's draw the uniform electric field. Let's say the electric field are here, equally spaced, but I did not give you the direction. So this is the x-axis. So electric field is either along the x-axis or the negative x-axis. So E can point in this direction or in this direction. We will see. So that's the question. Find the magnitude and direction of the electric field. So I want to find the magnitude and direction of electric field needed to stop the proton momentarily at a distance of 1.35 after entering the field. Good. Now let's draw the problem very quickly. Let's assume here I have my proton, which is positively charged, and it has an initial velocity, and I call it P0. And P0 is positive along x, 3.80, 10 to the power 6 meters per second. This is my initial speed. And then it enters this electric field. It goes for a distance of delta x, here delta x, and then it momentarily stops. So V final is 0 when it momentarily stops. When it stops, it will now return and go back. Okay, so here I gave you delta x, which is this distance here, and it's equal to 1.35 meters. So what can we say about the direction of the electric field? It's a positively charged particle, which is moving in the positive x direction, and I want it to stop. So I have to apply an acceleration, which is opposite to the velocity. So the electric force Fe is in this direction, which is plus E. This means that E, your electric field, is the negative x direction. So we answered the first question. E is in the negative x direction. So we know the direction. Velocity of the positive photon is in the positive direction. The acceleration is in the negative direction. The electric field is in the negative direction. The electric force is in the negative direction to make it stop. Great. Okay, now the question is, what is the magnitude? What is the magnitude of E? Okay, let's get the acceleration first. Since the electric field is constant, we can use constant acceleration motion equation. Okay, constant acceleration motion equation. So we say V final squared is equal to V initial squared plus 2 times A delta x, meaning A would be V final squared, which is 0, minus V initial squared, which is V naught squared, divided by 2 delta x. This will give me the acceleration. And I find an acceleration which is, let me write it down, minus 3.8 10 to the power 6 squared divided by 2 times 1.45. So this gives you an acceleration of minus 5.348 10 to the power 12 meters per second squared. This is the acceleration. But I don't want the acceleration, I want the electric field. What's the relationship between the acceleration and the electric field? If you remember, just Q E divided by M. So here, Q is plus E. E is in the negative direction. That's why you have a negative minus E divided by mass of the photon. And we know the mass of the photon is given. So we can get our electric field. So the electric field, using these two pieces of information, we can get our electric field. E is mass of photon times the acceleration. Don't forget the negative sign, okay? Minus the acceleration gives you a positive, because here I'm looking for magnitude, divided by plus E. 1.6 10 to the power minus 27, 67. Okay, 1.67 10 to the power minus 27 kilogram. You put everything in SI units. Times minus 5.35 10 to the power 12 divided by 1.6 10 to the power minus 19. Sorry. And this gives you an electric field of 5.58 10 to the power 4 meters per coulomb. So this is the magnitude. You do this, you get half of the point, and you say that direction E is in the negative direction. Meaning, if I write E in unit vector notation, E is equal to minus 5.58 or 5.60, 3 significant figures, 10 to the power 4 Newton per Coulomb. I have this is the correct answer. And we do this, we get 3 marks. Is it clear? Okay. Some of you will ask me, where did I get this formula for the acceleration? You know that the electric force, which is QE, will be equal to mass times acceleration. That means acceleration vector is QE vector divided by M. From here, this is how we got this. Okay, good. So I hope you did well. Wish you the best and see you next time.